Hello class. A few quick notes before we begin. The exams have been graded. Homeworks 1 through 3 and the midterms will be put on Blackboard, and drop day is Friday for those of you to consider dropping class if you're doing very poorly. Um, there will be curves on the exams. They just haven't been determined yet. Homework 4 is due tonight. Homework 5 is out. Yes, you do indeed have to find a 0 day through fuzzing, and to help you out with that, I'm going to cover what just came out on NetSeg earlier this week. A fuzzing project called Zulu Fuzzer from NCC Group, and it's pretty slick. There's a nice GUI that comes with it. It's entirely written in Python. And what you see in this GUI is on the left, this is an instance for network fuzzing network packets. It also supports file fuzzing, USB protocol fuzzing, serial fuzzing, and all sorts of other fun stuff. On the left, you see packets, and one of them is highlighted, packet 6. And for packet 6, you see the input data bytes, and some of these are highlighted as well. What's special about these is the fuzzer is being told for these segments in the packet, fuzz them. And so the following mutators have been selected: long string, format strings, etc., etc. And it's nice that the mutators is provided in the checklist. And so the mutation points are specified here, and one of them is specified as this is the length of the packet. And so it's smart, and it recalculates the length of a packet and provides that field accordingly, because say your mutator adds, instead of these 2 bytes, adds 4 bytes. Well, that changes the length and may cause the packet to no longer pass a basic constraint in order to get into the system. Speaking of a basic constraint, many things you will find that when you have to fuzz them have a hash to determine integrity of the file or of the packet, probably a CRC check that you have to calculate correctly. And so you may have to, after you're done fuzzing and mutating a specific input, recalculate the hash for that packet or the CRC check in order to get it to pass that basic integrity check constraint. So let's look at these mutators, because often a fuzzer's efficiency is only as good as its mutators. So the mutators for Zulu are stored in a flat text file, and you see it's just throwing all A's for the long string mutator. And for command injection, it's throwing all sorts of different Linux user commands, Unix commands rather, such as ID, we'll see ls, we'll see cat, etc password, we'll see ping. And then for format strings, these should all be very familiar from the previous lectures. It's going to, if this mutator is selected, put these in place of the input bytes, and perhaps that will trigger exceptional behavior in a format string vulnerability. Then there are all sorts of different null bytes depending on character representation and the input. There's XML attacks, and obviously these have much more information in them as opposed to just throwing all A's. So this demonstrates that there's a bit more complexity and perhaps more quality to this mutator than just throwing flat A's. And so you'll often find that your ability to trigger things with the fuzzer can be limited by how good or bad your mutators are. So if you choose to use Zulu Fuzzer for Homework 5, you may consider adding in your own mutational rules if you'd like. You may steal them from other fuzzers as you find them. Anyways, let's begin the lecture. So we left off last time with a demo on executing shellcode on a vulnerable stack example. And we're exploring how the stack works, well, more or less recapping that and showing how we're overriding the return address to point to shellcode that we stored in an environment variable. It's extremely toy example, very academic example that would only happen if a system were set up so poorly. But it was to demonstrate the very, very basics of a privilege escalation. So often you'll see that the stack, however, is not executable. So memory segments, as we discussed, have permissions. Usually you'll see read, write, or execute. And you'll often see that the stack, as it is the program's scratch space uh, for data, will not be set to executable permission. So if you store shellcode or you inject malicious code there and you try to point the processor to it, it's going to segmentation fault because it's trying to perform an operation or access a segment that doesn't have a segment of memory that doesn't have permission to do whatever it's being told to do. So you can still, however, control EIP because return addresses are stored on the stack, so you can still hijack execution and point it somewhere else. So you can point it to other segments that have executable permission that you can perhaps inject code into. You can also point it to existing code and get it to operate maliciously. For instance, you can point it to all sorts of library code, and one of the most common libraries is libc. Libc has lots of fun features to make general C programming much more enjoyable, such as allowing you to make arbitrary Unix commands with the system, not the same as system calls, as we'll cover later. And in order to spawn a shell and do the same example, what we'd have to do is pass system an address to a string that's contained bin sh in memory. And we're going to explore how, for this given stack where we have the previous function as passed argument 2, argument 1, its return address, and then jumped into the function, and the function prolog pushes EBP, pushes its own local data, and then the vulnerable buffer, for example. And this will be, these top three will be the prolog actions, and the prior things will be assumed by this function to be handled before calling it, and that's the calling convention. So we're going to exploit this. Let's go full screen. So the first thing we're going to do is we're going to fill up the vulnerable buffer all the way up to the return address with garbage data. Instead of just completely smashing the stack, we got to be a little bit more precise here. So we overwrite the return address on the stack with the address of system. We're going to have to find that. And then we follow system with whatever we want it to return to. So we're going to have it return to exit. And exit will have it exit all cleanly. If you don't exit all cleanly, it may cause your exploit to crash or to fail to pull off. And then we're going to pass system the very first argument. It's very, very simple, very, very sweet. So this is, again, the unattacked stack, and we're going to target this and then pass it a new return address, and then argument 1 is going to go here. So we fill it up with garbage data all the way up to the old return address, and we replace that with system. So when this vulnerable stack frame returns, it's going to turn it into system, and system's going to assume that the first thing it sees on the stack, because ESP is pointing here, is going to be the return address for it. So we've passed it exit. And then 4 after that, in a 32-bit system, 4 bytes after that, would be argument 1. So what we're going to do is effectively have to locate the addresses of system, address of exit, and address to a string in memory for bin sh. So if you do not pass a new return address for system, like I said, it may cause the exploit to fail and perhaps to behave weirdly or fail some % of the time. And we're going to actually have a demo on this later when we go into code reuse attacks. But for now, we're going to dive into, the next lecture. And I have a number of demos recorded to record for this one. So last time we covered the world's largest DDoS attack going on at the beginning of the lecture. And this is actually a very good article on the very basics of the technique they used, NTP amplification. The article also covers how to defend against it and how to identify if it's going on your servers or your networks, and how to determine if your servers, if their NTP servers, are vulnerable. It's a pretty quick and easy and good read. Speaking of botnets, there's also another good article on attacking financial malware and the botnet command and control panel. And we'll cover these attack techniques, but it goes to show that hackers aren't always good at security either. So the FBI every now and then brings down a really, really big botnet. I believe they brought down a number of Zeus botnets, and hacking the single point of failure, one of the command and control panels, may be the way to do it. And so this author found, I think he was just playing around with it for one evening. He found the following vulnerabilities that are actually quite boring in the command and control panel, such as the HTTP doesn't have, the login panel doesn't have HTTPS, so it sends all the credentials over plain text. Is very easy to brute force. There is no cross-site request forgery protection. The passwords are stored in MD5. You can do SQL injection on the login page, and we'll cover these techniques later. And the fun one he found, which is where this stuff is more relevant, is he was able to find a remote code execution vulnerability in the command and control interface for the botnet, and it allows him to, with PHP, simply hijack the botnet, which is pretty awesome, or at least compromise it. So it's a good read, and we'll get into this stuff later. And this exploit development lecture is teaching the basics of this stuff in C and x86. However, all the approaches definitely apply for higher order languages like Python, PHP, etc. So for the outline of the rest of today's lecture, we're going to cover the foundations of writing shellcode and really dive into it for Linux, and then end today's lecture on position-independent shellcode. And next time we're going to cover heap exploitation and the rest of this stuff. And we'll get into ASLR, DEP, NX, SEH, SEHOP, the ways they're attacked, and the protections they provide, and how valuable they are. So a good resource for the slides is the Shellcoder's Handbook, as well as the Art of Exploitation textbook. Shellcoder's Handbook is decently up to date. Is growing old though, and it's important to cover this stuff because exploits and shellcode doesn't rain from the heavens. So like every now and then, oh my God, there's no day. Let's plug it into Metasploit. It takes a moderate amount of skill to develop exploits. Often, for very harder ones, it takes an immense amount of skill. And so there are a lot of tools in this domain. Often a hex editor is going to be one of your most commonly used tools, as well as some sort of assembler, some sort of disassembler, some sort of compiler, some sort of debugger, a linker, something for also editing raw data like a hex editor, perhaps just for extracting. DD is useful for that. And some form in which you can test your shellcode. The above tests, I believe, just simple shellcode, networking shellcode written in C and x86. And there can be different syntaxes for the instruction set of your choice. For x86, there's commonly AT&T syntax and Intel syntax. And as our guest lecturer said, that most everyone nowadays uses Intel syntax. So if you're using GDB, the way to set it, because it defaults to AT&T syntax, which can be confusing if you're coming straight from the slides and straight from the Art of Exploitation textbook. I should note that the other textbook I suggested, Shellcode, The Art of Exploitation, the Shellcoder's Handbook, I apologize, prefers AT&T syntax. To set your syntax flavor, you basically do set disassembly flavor, Intel or AT&T. For GCC, you tell it Intel. For NASM, the default is Intel. For object dump, the default is AT&T. So you capital M, Intel will tell it to disassemble in Intel syntax for x86 instructions. So shellcode is a set of instructions that's injected and executed by a vulnerable program in an exploit. And originally, the main purpose was to spawn a shell. It now refers to any exploit code at this level and is used to directly manipulate program registers, processor registers rather, and the execution of a program. It's thus generally written in assembly code and then translated to hexadecimal opcodes by assembling it, linking it. And there are often very subtle nuances that you have to pay attention to when working at this level. And these nuances are often processor specific, operating system specific, and then sometimes they can be also library, compiler, and virtual machine, sandbox, etc. specific. And we're going to have to learn how to write our own shellcode so that if you see it, not only in a pen testing standpoint, but also an incident response standpoint, you are able to identify it, reverse engineer it, and figure out exactly what the attackers are doing to your system. That's why we're covering it. So in order to understand how to write shellcode, we're going to have to understand system calls. This is not the same as the previous example that I started with, system function provided by libc, or any other library calls. System calls are provided as an interface to the operating system. You should remember that. They're very different in A, style, B, calling convention, and C, functionality than functions provided by libraries. They often also completely differ per operating system. So system calls are extremely powerful and allow access to operating system level functions. And in order to trigger them, usually the processor has to switch from user mode to kernel mode, and that requires a full context switch, some performance overhead as well. So there are two common methods for executing a system call in Linux. You can call the libc wrapper, so execve, etc. Well, I'm sorry, that's the system call directly. Or you can call the system call directly with assembly. So you load the appropriate arguments on the stack, and then you call interrupt 0x80. So int 0x80 is the most classic way of directly calling system calls in assembly. There are alternative methods that I've heard of in different trap numbers, interrupt numbers rather, and we'll touch on them just a little bit. Okay, slides, you need to behave. Okay. All right, presentation software to slow things down. Okay, so when intox80 or int0x80, I just call it intox80 for short, is executed by a user mode program, the CPU switches into kernel mode and executes the function. The function is specified usually by some sort of index into a table of system calls. So for Linux, this can differ from standard Unix, as Linux implements the fast call convention for calling system calls. and this provides somewhat higher performance. And effectively, the specific system call is loaded into EAX register. Instead of being put on the stack as an argument, it's loaded into the register. And then the rest of the arguments are placed into EBX, ECX, EDX, and etc. Um, for if you pass it enough arguments, they will start being put on the stack. And then the instruction intox 80 is executed. CPU then will switch to kernel mode, and the syscall function will then begin executing. So each system call has a unique integer value, and let's jump to a system call table for, what is this? Oh, the Linux 2.2 kernel. So this is a little outdated, but it gives you an example. So if you were set EAX to 1, that would specify the exit system call. If you set EAX to 2, that would specify the fork system call, etc., etc., etc. And this table specifies what EBX will contain, ECX, EDX, ESI, EDI, etc. I don't believe anything goes, nope, some things may go past EDI, as I suggested. So, with that under our belts, often the registers, instead of containing an entire string or an entire structure, will contain a pointer to whatever it needs. And that's the common way of doing things, even on the stack. So the most basic, absolutely basic system call is exit. It takes in one parameter, and it then just calls intox 80 after setting EAX to 1. So let's see how this works in assembly. I have some very basic, oh, that's too soon. For this code, if we compile this, it will disassemble to the following code for the function exit. It will move EBX some value, then it will move EAX to OXFC. Obviously, this is a different. And then it will run this, and then it will move EAX1. And you can see there are two system calls. It's been a while since I updated these slides. So what's going on here is that it's doing some system call here for the handler for exit, and then finally running exit. So this previous system call, whatever FC is, I could look it up, but it hardly matters, is obviously doing some form of cleanup, and it's indexed in the system call table specified as FC, and then its first parameter is being passed here. So OXFC is 252, and this corresponds to exit group, so it exits the group for the process and then exits the rest. Very, very simple, and it illustrates how this works. So, what we're interested in is triggering this with raw instructions and injecting these into a vulnerable process. And in order to do this, you may have to be aware of the other ways that system calls may be pulled off. As I said, the intox 80 classic implementation has a very high overhead, and there have been some optimizations added in the forms of alternatives. As at the start of Pentium 2, Intel added in sysenter as a alternative for intox 80. So if you call sysenter, it will handle similarly. Also, AMD similarly put in syscall, and then Linux at the 2.5 kernel iterations began with the free syscall page. Basically, virtual system calls and the virtual system call page are maintained by the kernel, allowing for faster running of kernel mode stuff without so much overhead of the full context switch, if I recall correctly. It's also important to keep in mind that compilers may do all this stuff differently, so that's another nuance to be aware of. So let's write some shellcode just to pull off the basic exit. So we're going to want to store 0 in EBX, we're going to want to store 1 in EAX, and then we're going to want to call int 0x80. And so the following assembly code will perform this. We set the start function to first run move 0 into EBX, then move 1 into EAX, then to call int 0x80. So if you save this as exit shellcode.asm or something.asm, you'll use the NASM assembler to create your object file. There we go. And NASM-FELF will tell it to specifically to create a ELF format executable, and then the loader will load in the rest. And when we go to disassemble it with object-dump, you're going to see that these are the corresponding opcodes for each of these instructions. So move EBX 0, move 0 into EBX is BB 00000000. So it's 5 bytes wide. The next one is 5 bytes wide. The next one is 2 bytes wide. It's rather simple. So when you convert this into a character string, you're going to have in C the /x escapes and tells it to specify that the following 2 characters as a raw byte, obviously limited to 0 through 9, A through F, to BB /x BB /x00 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 /x00, and so on and so on and so on. Very, very straightforward, but this is an important concept to understand. So given the following code, I have it running here in this VM, if we tell it to compile it and then we run it, we can't really tell what it's doing. We're telling it to exit right away. So what we're going to have to do is trace the system call to see what's going on. And you'll see that the very last thing that's being called is indeed exit. However, this works. This is great. However, there's a problem. If you try to enter this into a buffer for a vulnerable program, this is not going to work. You have null characters, and any string copy operation is going to terminate on the first null character it finds. It doesn't care what happens what occurs in the string after that. You could have the rest of your payload. It's going to truncate it right there. So null bytes are a specific problem for string copy and often array-oriented copy operations. Anything that relies on terminating on a null byte or any other terminator has this style of problem. So this would be completely unusable in a real-world exploit. So there are 2 common methods to get around this. You can replace the assembly instructions with other instructions that create nulls accordingly, but those have to all run prior to it. And that's going to be self-modifying code. Or you craft the shell code so that there are no nulls at all. So either you add the nulls in at runtime, or you craft it so there are no instructions that have null bytes. So you replace any assembly instructions that have null bytes with instructions that do not. So this involves playing with things like XOR, playing with the subparts of registers like the lower half, upper half. And we're going to cover the the art of self-modifying code actually in this one is in this lecture as well. It's not too difficult actually. So let's replace these instructions with similar instructions that don't have any null characters. And a very, very useful tool for this is something provided by Metasploit called NASM shell. And you'll usually find it titled nasm_shell.ruby, and you can find it with this command Metasploit running backtrack. And so we'll see that move EAX1 produces the opcodes B8, 01, 00, 00. These trailing 0 bytes are the problem. Anything that precedes it is actually not a problem. To clarify, this specifies the line number, so this is line 0. So if we do like XOR, EAX, EAX, and then INC EAX, that would be one way to set EAX to 1. Another way would be to move perhaps into the lower byte 1, and this does not produce a null byte. You do see two zeros side by side. However, this would be the first byte, and this would be the second byte, and that's the way the things are aligned, period. So, the way we rewrite these is instead of moving 0 into EBX, we XOR EBX, EBX, and then instead of moving 1 into it, we can move 1 into the AL register. And to recap, the AL register is the lower 8 bits of the AEX or RAX register, and this is left over from the very, very old days for backwards compatibility. And a lot of things that are left in for backwards compatibility are often very convenient during exploitation. And backwards compatibility is often one of the absolute banes of security, and is really frustrating to have to defend legacy and backwards compatible stuff. So this is our new assembly code, and you'll see that when we put it all together, there are no null opcodes, and this is great. The shellcode is also much smaller, and this is actual shellcode that you could inject into a vulnerable process, this buffer, that would cause it to exit. Not very useful. So let's recap here that there are 5 steps I suggest for writing useful shellcode. You first use a high-level language to write the desired shellcode, and we're going to explore another example with that. And you compile and disassemble a high-level shellcode program. You analyze how it works at the lowest level, the assembly level, and you clean it up, you compact it, you make it injectable, you extract the opcodes to create the shellcode, and you should be good. So let's start from a basis, and we want to be able to execute arbitrary binary. And this would be the code to execute binsh with execve. And execve takes 3 arguments: a pointer to a string that specifies a file name, pointer to an array of arguments, and then a pointer to an array of environment variables, which can often just be completely null. So what we need is position-independent shellcode that we can inject, because when we put something into a process that we're targeting, we usually cannot attach a debugger to it. We usually cannot figure out without a memleak what the stack looks like at a specific address. And so we need some way of having it so that our shellcode is not fragile and doesn't rely on it being located at a very, very specific address in order to work. It needs to be position independent. So this is a difficult task, but there are ways to do it, and usually short jumps allow you to do this, and we're going to explore that in just a little bit, but I don't want to get too far ahead of myself. So, like I said, exec_VE, this is the target system call. We're going to use this to spawn a new shell. It takes 3 arguments. They must all be pointers. The first argument is going to be a pointer to a string. The string specifies what it's going to execute. In this case, it's going to be bin sh. The next pointer is going to be to an arguments array. And in most cases, the very first argument is just going to be also the name of the file. Then a pointer to the environment array can be left as completely null, will have to be pointed in as well. So EAX is going to be the system call for exec_VE. EBX is going to be a pointer to the string in the binary to execute. ECX is going to be a pointer to the arguments array. And EDX is going to be a pointer to the environment array, or a pointer to something that's null. Not a null pointer, but a pointer to something that is null. So, like I said, hard-coded addressing makes fragile shellcode, and relative addressing makes position-independent shellcode. And so, EAX will hold the integer number for the address of the exec_VE system call, and we've already covered the rest of this. So, what we're going to do is take the C code that we've shown on the previous slide, compile it, and we're going to look at it. And this may be really intimidating to look at, but bear with me. We're going to use this to help us understand what to do. So, looking just at exec_VE, because this is where the action occurs, we see that it's moving into EAX, the value OXB. Then the next things, judging by the arguments to this, is that this is the second argument, and it's moving it to EBX. This is the third argument. No, this is the third argument, and it's moving it to ECX. And this is the fourth argument, and it's moving it to EDX. And then it calls int 0x80, and then boom, it's done. So we're going to have to find some way to hold the address, to hold the string bin sh and have it be null terminated. And we're also going to have to find some way to hold a null terminated array of arguments. We're only going to need one argument, the program name. And we're also going to have EDX point to a null terminated environment array. So there's a lot of nulls we have to add in. Obviously, we can't just have them statically in there. So let's walk through this assembly code that is not only position independent, but does all of this, almost. So the first thing that it does is say when the processor jumps right here, all right, it's going to set the return address to wherever it was previously in the .text segment. Say we're storing this on the stack. So the return address is pointing there. The stack pointer is pointing somewhere perhaps independent of this. And if we tell it to short jump allows you to jump forward or backwards by X number of bytes. It doesn't require jump to exactly this address, which would be hard-coded addressing. It is instead relative addressing. So short jump is the way to go. So we're going to short jump down to part 2, and when we put this all together, it determines exactly the number of bytes to do this, and we don't have to calculate it by hand. And then what we do is we call part 1. By jumping back here, we set it up so that this point is pushed onto the stack as a return address. And so if we use it accordingly, we can manipulate the rest of this string. So let's keep that in mind as we go forward. If we pop the stack at this point, this is going to have the address of our string because it's going to have the return address. And normally here is where you would expect the function prologue where it saves EBP it moves ESP to the appropriate place, and then it's making room for the local variables, and then it sets the local variables, etc. Instead, what we're doing is we're exploiting the fact that call saves the return address. So by popping the first thing, we're going to pop the address here. So EBX now has the address to a string that contains bin sh. However, it has all this extra crap on it. This is just a dummy placeholder to demonstrate what we're doing. So we're going to zero out EAX. And then what we're going to do is, with EAX now as the null register, it contains all zeros. If we move 1 byte, 8 bits, into EBX plus 7, so that's 1, 2, 3, 4, 5, 6, 7. So EBX would point here, so 1, 2, 3, 4, 5, 6, 7. If we replace X with 0, then we're great. So then this has now been null terminated by this operation. Now what we want to do is move the string EBX, the pointer stored in EBX now, to EBX plus 8. So it's going to overwrite 1337 with the address also to bin sh. And then what we do here is we put EAX, which has been 4 null bytes because it's been zeroed out. We now overwrite all of B055 with a null terminator. So it's completely null terminated. So we now load the effective address for EBX plus 8 into ECX. So ECX is now pointing to where 1337 has been overwritten. Okay? EDX is now being overwritten with a pointer to zeros. So it's pointing to a null D word. That's perfect. ECX is pointing to an array, and the first thing is pointing to bin sh. The next thing, it looks at the next D word, is, oh, that's already been zeroed out. So we're using the B055 here twice. We're using it once to terminate the array for ECX, and we're using it again to be just a null terminated array for EDX. Brilliant. Then we set up EAX to have the appropriate system call number, and we call intox80, and that's what we'll launch. Hopefully you all understand that. So when we put this all together and we look at it, there's going to be a problem. If you just look at the binary, there's 0 standing all alone, and we won't be able to inject this into a burnable buffer. So we're going to have to make a little bit of modifications, and this is pretty typical when you're writing shellcode, having to do this step. As a note, if I haven't said so already, if you just run NASM as without any file specifier, it's going to create raw binary, and if you try to look at it, it's not going to know what to do. So you're not going to be able to do anything like object dump disassembly with it. It'll tell you file format not recognized, which is why we're looking at it with text dump. So blah, blah, blah. So when we look at it, the null bytes are specifically caused by move 11 or 0xb into EAX. And we're going to find some way to move 11 into EAX without triggering these null bytes. So, blah, blah, blah. We move it into AL. And what that gives us is success. Also, the shellcode, I believe, is shorter. So we have the following shellcode, and we now have move AL and move 11 into AL, and we're going to, whoops, this is the right terminal. See that it indeed has no mouse. Stop messing up. I hate this VM. It has no null bytes, and say we have this process dot slash. We have this process form, and it does some form. Oops. Something, and if we give it a very large string, perhaps it's going to crash. Indeed, it's seg faults. So what we're going to demonstrate is the efficacy of this position independent shellcode, and I have it somewhere in yes. Alright, so let's indeed verify that there are no null bytes, and we can see that it looks like there are no null bytes. So just for the sake of demonstration, we're going to again put this in environment variable and just demonstrate really simple, crappy priv-esque. Whoops. Alright, so we're going to again get the environment variable of vuln, of shellcode in vuln, and so if we run vuln now, this is assuming we can view the environment, the stack of vuln, and we tell it to smash the stack with the address to point there, we're going to pull this all off, assuming everything aligns correctly. And we'll discuss that more later. And boom, it worked. So the shellcode spawned via execve system call in a position independent manner by using short jumps to rely on the fact that when you do short jumps and calls, that it's going to put a stack address in a reliable place on the stack that you can then use in a relative manner. So that's going to be it for this time, and we're going to cover the rest of all this good stuff later.